Hello, and this video lesson is on carboxylic acids, and from the picture you can see a lemon tree, so I think you can see the connection there, citric acid being the connection, which is a carboxylic acid. And so we're going to find out in this video what carboxylic acids are, and then we're going to look at their physical properties. We're going to look at the salts of carboxylic acids, just like normal mineral acids. When they react with alkalis, they can make salts. So do carboxylic acids. And then we need to see the acid reactions of carboxylic acids. Carboxylic acids occur naturally in nature all over the place. For example, ant sting is methanoic acid. Have you ever smelt a goat? Well, goat smell comes from hexanoic acid. And you're very likely to be wearing now or soon some nylon. Nylon is a condensation polymer made from carboxylic acids. And here we have some soap, some cosmetics, and some biodiesel, all of which are made using carboxylic acids. So here let's study what are carboxylic acids, and we can draw the functional group. So again, we're going to have an alkyl group connected to an alpha carbon, which has the carbonyl group on it. But as well as the carbonyl group, we also have a hydroxyl group. And what I want to do is I just want to draw the bond between the oxygen and the hydrogen in the carbonyl group for a reason you'll see in a minute. So this is the general structure of a carboxylic acid, and the functional group is this that I will circle in red, and that is written COOH when you write in a structural formula. Now carboxylic acids are weak acids, which means that not much dissociation happens. So for example, if you've got, let's start off with methanoic acid. If you've got methanoic acid, which is just the one carbon, so you can have the acid group here. And if it's methanoic acid, we've got no alkyl group, it's just a hydrogen. That saves me drawing it out a little bit. And when you dissolve that in water, you get an equilibrium reaction between the methanoate ion, which is drawn like this. That's got a minus and a H plus. So you can see that when it dissolves in water, this bond here that I'm underlining in red has broken, and the electrons, let's draw them in, the electrons that were in that bond have both gravitated towards the oxygen, which has led to this minus charge because oxygen's now got that extra electron that was with the hydrogen, and hydrogen is no longer with an electron, and so it leaves as a hydrogen ion, which is of course what makes the solution acidic. But this equilibrium reaction is way over to the left hand side, so most molecules, most of the acid molecules stay undissociated. Undissociated just means that this bond here hasn't broken and they're complete molecules. So the equilibrium lies over to the left with carboxylic acids, in contrast to strong acids. Let's take HCl. Now when that dissolves in water, this bond breaks completely, and so you don't even draw it as an equilibrium reaction, you just draw it with a normal arrow, giving you a hydrogen ion and a chloride ion in solution. So that's what happens with a strong acid. But here we've got weaker acids. Okay, let's talk about naming some carboxylic acids. So let's name and draw the first four. So the first one being methanoic acid, which we have done briefly already. So methanoic acid is functional group is going to be COOH. H, but in methanoic acid we've only got the hydrogen, and so we can quickly draw it like that. Ethanoic acid, as well as having the same functional group, which all of them will have, we're going to have a methyl group hanging off this carbon. So actually draw it like that to show the carbon-carbon bond, and then we've got our acid group as usual. Propanoic acid is going to have the same functional group, and it's going to have a CH3CH2 group on it this time. And that's drawn like this. And butanoic acid, should we just do butanoic acid? Tell you what, let's not do butanoic acid, it follows the same pattern. But what I will say that when you're naming, we're going to, the number one carbon, the alpha carbon, is the carbon that is involved in the functional group, and that would be the number 2, and that would be the number 3 carbon there. So let's start from a structure at this time and then name it. So let's say this is our acid. One, two, three, four. Let's have 5 carbons. Let's have our acid group. It's going to be on the end because the alpha carbon needs 4 bonds in its acid group. But as well as that, let's have a methyl group hanging off one of the carbons, like so. So why don't we name that? Well, first of all, we're going to pick the longest chain and then number the carbons. So this, as we said, is going to be carbon 1. That's going to be carbon 2, 3, 4, 5. So we've numbered the carbon, so it's going to be pentanoic acid. So let's write that down. And we're going to have a prefix to it as well, because we've got that methyl group there. So we're going to draw it over to the right. So pentanoic acid. And you can see the methyl group is hanging off the 4th carbon, so it's going to be 4-methyl. Methyl pentanoic acid. So there we have it. We can move on now, after we've named carboxylic acids, onto the physical properties. And when we're looking at the physical properties of carboxylic acids, the ones that we're interested in are solubility and boiling point. Both of which depend on the hydrogen bonding in the carboxylic acids. So let's draw the hydrogen bonding when a carboxylic acid dissolves in water. So let's have ethanoic acid rather. It's drawn out like this, of course, and we're going to have a partial negative charge on our oxygen here. We're going to have a partial positive charge on this hydrogen here for the electronegativity difference reasons that we're familiar with. If we want to be complete, we can put the delta positive on the alpha carbon. And so this, we're going to have molecules of water floating around, and they might look like this. And they're also going to have their partial charges. And so let's draw another water molecule down at the bottom here. And its partial charges. Like so. And so you can see there's going to be hydrogen bonding between the ethanoic acid molecule and the water molecules, like so. Those bonds, as you know, let's just label them as hydrogen bonds. They are hydrogen bonds, as we know, and that means that the ethanoic acid and the water molecules can mix very well, and explains the solubility of the short chain carboxylic acids. As with our aldehydes, ketones and alcohols, when the alkyl group gets longer, then the solubility decreases for the same reasons, in that the non-polar part of the molecule dominates, and means that they're less soluble in water because fewer hydrogen bonds are made. Okay, so that is all we need to say about solubility. Let's have a look at boiling point as well. Now, what we can do is we can have a look at chart, which is down the bottom here, and that's got boiling points of propan 1-ol and ethanoic acid, which you see from this column here have the same MR, but the boiling points are slightly different. Of course, we can see that the acid is greater boiling point than the propanol. So they both have hydrogen bonds. When we looked at the alcohols, we were quite familiar with the hydrogen bonds in the alcohol, holding the alcohol molecules together, requiring quite a lot of energy to break them apart, hence the high boiling point. But in the ethanoic acid, the boiling point's even higher, and it's still bonded with hydrogen bonds. So what can explain that difference here? That difference is caused by the fact that ethanoic acid molecules are going to make dimers, and the dimers are going to be twice as long, and therefore the van der Waals forces between molecules that are twice as long are going to be greater than the propanol molecules, which are half as long. So let's draw the formation of this dimer. So we're going to just draw a normal ethanoic acid molecule like we drew before. And let's draw in all the hydrogens just to be complete. And now we're going to draw an upside down ethanoic acid molecule. Like so. It doesn't think it's upside down, it doesn't think at all actually, does it? So we can see the hydrogen bonds are going to exist between here and here, and they're not covalent bonds, so it's not a dimer strictly, but hydrogen bonds are quite strong, and so it acts like a dimer. They do go around in a pair and don't dissociate so often, and so you can see that this molecule is quite long, and therefore the van der Waals forces is going to be greater, and that's what explains this boiling point of 118 that is higher than the boiling point of something that just has the same hydrogen bonds but less van der Waals. So you remember when we were dealing with mineral acids before and we reacted them with metals, you got a salt. So for example, when we had nitric acid reacting with a metal, we would make a nitrate, so it would be the metal nitrate. When we had sulfuric acid, you react that with a metal, you get a metal sulfate. And hydrochloric acid gave us a chloride, metal chloride. Okay, and so the salt, the second part of the salt name took those suffixes there, and when we do the same for a carboxylic acid, we call it a carboxylate. That's the generic term. We'll look at the individual terms in a second. Carboxylate. And so let's illustrate it with a diagram again. So we'll draw ethanoic acid. Like so. In fact, let me change the colour of the hydrogen to red. Okay, so there we have ethanoic acid, and just like in any acid reaction, we're going to lose that hydrogen, and when we do so, the anion that's left is called, in this case, ethanoate. Alright, so let's draw it out. We're going to draw it out in blue. So the rest of the molecule is the same, but the two electrons in that oxygen-hydrogen bond stayed with the oxygen, so it's got an extra electron now, giving it a negative charge. The hydrogen's gone, and if we reacted it with, say, sodium hydroxide, for example, we would have a sodium ion that would replace the hydrogen. And the hydrogen would go off with the hydroxide ion and make a water molecule. Okay, so this molecule here is called ethanoate. Right, and because it's bonded with sodium, it would be sodium ethanoate, would be the name of the salt. Sodium ethanoate would be the name of the salt. Now, a thing to notice here is that when we're drawing these salts, you don't draw a bond between the anion and the cation because it's ionic, it's not covalent, it's an ionic bond. So we just leave it like that if we need to draw it. So let's have a look at the first few names of the salts. Okay, so if we've got methanoic acid, then we're going to make a methanoate salt. So if it was, if you were reacting it with sodium hydroxide, for example, you'd be sodium methanoate would be the salt. This methanoate is the name of the anion of the salt, and likewise, ethanoic would be ethanoate, propanoic, propanoate, butanoic, butanoate. You get the idea. Okay, so that's the name. That's how to name salts of carboxylic acids. Okay, now we'll study the acid reactions of carboxylic acids, and they react in the same way as normal mineral acids do, like we've seen before, but because they're weak acids, the rate of reaction will be a bit less. But you remember that mineral acids react with carbonates and give yourself carbon dioxide amongst salts and water, and so do carboxylic acids. So let's have a look at their reactions with carbonates first. So let's use a real example. Let's use ethanoic acid. So CH3COOH is the way that we write ethanoic acid out, and we might want to react it with sodium carbonate, for example. So while we're doing it, let's work out the formula of sodium carbonate. The carbonate ion, you know, is a 2- ion. The sodium ion, you know, is a 1+ ion. So you're going to need 2 sodiums to match the charge on the 2- carbonate ion. And when they react, you're going to make a salt, you're going to make carbon dioxide, and you're going to make water. So the salt is going to be sodium ethanoate. So let's just revise that a little bit from the previous slide. That's going to be our ethanoate ion, and our hydrogen is going to go off and make some water. And we're going to take one of those sodiums, and that's going to be linked ionically with the ethanoate ion. So sodium ethanoate, you can write the ethanoate ion first if you like. So that's the CH3COO minus charge, but we don't write the minus charge in the reaction equation, and that's linked ionically with the sodium, 1+ ion. So that's sodium ethanoate. So the carbonate, this carbonate ion here breaks down, and so we get some carbon dioxide coming off. Alright, but we've got one of those three oxygens still to account for, and that goes in, forms a water molecule with hydrogen. So we're going to need two of these two hydrogens to make the water molecule. So to balance this, we're going to put a 2 there, and that requires a 2 there. We already had 2 sodiums, and we've got 2 sodiums on the right hand side. We've got carbon dioxide is balanced and water is balanced. So that's our equation for a reaction with sodium carbonate. Let's do another carbonate reaction. Why don't we do sodium hydrogen carbonate this time? So we're going to have ethanoic acid again. This time let's react our let's make our carbonate sodium hydrogen carbonate. So we only need one sodium because hydrogen can do the job of the other sodium. And again, we're going to get the same salt. We're going to get sodium ethanoate. That's our ethanoate ion. That's our sodium ion. And you're going to get your carbonate breaking down into CO2 again. And now we're also going to get a water molecule, but that's already balanced because the hydrogen from the ethanoic acid has combined with the hydrogen from the sodium hydrogen carbonate and the oxygen from the carbonate ion and made the water molecule. So we're all done there. So that's how carboxylic acids react with carbonates. The other acid reaction that we need to focus on is, let's write down carbonates up here, and we also need to study reaction with metals, acids plus metals. So let's do that here. But before we do, let's just backtrack a little bit and mention that that reaction with carbonate is used for the test for an acid. So if you've got a solution and you think it's an acid, you want to confirm that it's an acid, you're going to add a little spatula of either sodium carbonate or sodium hydrogen carbonate to it, and what you'll find is you'll get effervescence like that, which we're suggesting is carbon dioxide. And to show it's carbon dioxide, you would bubble that gas through lime water, which of course would go cloudy and confirm that it's carbon dioxide. So that's the test, if you remember, for acids, i.e. add a spatula of sodium hydrogen carbonate or sodium carbonate. Okay, back to metals. How do carboxylic acids react with metals? Again, the carboxylic acids are going to react in the same way with metals as mineral acids did. So let's use ethanoic acid again. CH3COOH is our ethanoic acid. This time we're just going to react it with a metal. Let's choose magnesium, shall we? And in the usual way, we're going to get a salt plus hydrogen this time. So just like before, we got salt plus hydrogen. With carboxylic acids, we're also going to get hydrogen. So our salt is going to be, this time it's going to be magnesium ethanoate. So again, we can write our ethanoate ion first, unusually, because of course usually the cation goes first in the salt. So here's going to be our ethanoate ion, CH3COO. That's a minus charge. That's going to be bonded with a magnesium. It's in solution actually. So the magnesium ion, you know, is a 2+ ion, and the ethanoate ion is a 1- ion. So we're going to need 2 of those to make the salt. And the hydrogen that was in the acid is now given off as a gas. So we're going to see bubbles of hydrogen coming off this reaction mixture. And in order to balance this, we just need to put a big 2 there. And now that's good. So just just to reiterate, you've got your acid, ethanoic acid in this case, reacting with a metal, magnesium in this case, giving our salt, which is magnesium ethanoate plus hydrogen. And again, you could do the squeaky pop test on the hydrogen to confirm it was hydrogen. Okay, so there's our reactions with metals. Let's also do, while we're at it, reactions with bases, which include alkalis, of course. So a reaction with bases. Let's stick with ethanoic acid, but this time let me do this reaction in green. So we've got our CH3COOH for our ethanoic acid. This time we're going to react it with a base. Let's choose sodium hydroxide, a soluble base, which is known as an alkali, you'll remember. And just as before, when you react an acid with an alkali or a base, you're going to get a salt plus water. In this case, our salt is going to be sodium ethanoate again. So again, we're going to write our ethanoate ion out first, CH3COO, and that's got a minus charge to it, and our sodium's got a plus charge to it. So there's our salt, and we need some water, which is H2O, and one of the hydrogens has come from our acid, and the OH group has come from the hydroxide of the sodium hydroxide, and that's made our alkali, water rather. And what you would observe with this reaction is that it's quite exothermic, so you get a release of heat. The temperature of the reaction mixture would increase before that heat is lost to the atmosphere, but the colourless solution remains. Okay, so why don't we do another reaction with the base. Let's take ammonia, for example. So our ethanoic acid again, CH3COOH. Let's react that now with ammonia. Ammonia is NH3, you'll remember. And when we do that, what happens is we get a reaction between the NH3 and the hydrogen of the acid, and that makes an ammonium ion, which is NH4 plus, and that's the cation that is part of the salt. The anion part of the salt is the ethanoate ion, as usual. And for this case, I will just put the charges. That's our -1 charge on their ethanoate ion, and ammonium ion has a 1+ charge, and so that's balanced, and so the formula of that salt is good. So that's what you get when you react a carboxylic acid with ammonia, and that's the only product. We don't get any water off, because that hydrogen is just combined with the whole of our ammonia molecule. And in this case as well, you won't see much happening because the reactants are clear, colourless, and so is the product. But you will get heat given off. It's an exothermic reaction, and you would notice the temperature increase. And just to finish off, let's just check that we have covered off everything we intended to. What are carboxylic acids? Well, they're acids with the COOH functional group. We named them as well according to normal rules. Physical properties, we looked at the solubility and the boiling points. Hydrogen bonds and diamonds were the key points there. We looked at salts of carboxylic acids, especially ethanoate ions, and we know how to name them as well. And we also had a look at the acid reactions, the reactions with carbonates, making carbon dioxide, with hydrogen, with metals rather, making hydrogen, and the exothermic reactions with bases, in particular the two alkalis that we used. Okay, there we have it.